Let's take another look at the example we have when we talk about the linear transformation. Here we have this black vector, and when I transform this black vector by a linear transformation, in this case multiplying by the matrix M here, I obtain this orange vector. Now, if you play around with this black vector thing, you try to move it around, you will see that the orange vector will actually kind of move along. So now you might ask, will it ever be possible that the black vector and the orange vector is actually the same vector? And once you play around with it for a while, you will see that this is actually not possible no matter how big or how you move around the black vector. The orange vector seems like it's one step ahead of the black vector. So, having the black vector and the orange vector being the same thing, it just doesn't seem possible. So let me kind of tinker around with the matrix M here a little bit. Let me just change, let me change one of these values here. So, actually, we get a different transformation now. And it seems like my black vector, oh how lucky, is in the same direction as the orange vector. Let me kind of move this around. So it actually doesn't happen often. So when my black vector lies on the x-axis, it seems like my orange vector will be on the same direction. Let me try to move it around. Okay, here's another one. When my black vector is around here, the orange vector seems to have the same direction as the black vector. And then it happens again here. Let me try to move around a little bit more. It happens again here. So this is the opposite direction of what we see earlier, by the way. So we actually see it kind of happen in two of the direction on the x-axis or on this kind of invisible line here. So this kind of thing, it actually has a name. It is actually going to be pretty special later on. But for now, let me just show you the first example that we have here. Okay. So we have a matrix A, which is just 3315. And I like to find all vectors V such that A times V is 2V. So, okay, let me just go ahead and solve this thing. This shouldn't be hard. So I have my matrix A times V equal to 2V. And I knew that my matrix A, this would be just 3315. My vector V, let me call it V1, V2. That should be 2 times V, which is V1, V2. Now then, let me multiply my left-hand side here. So this would be 3V1 plus 3V2. And then the bottom coordinate would be V1 plus 5V2. V1 plus 5V2 equals 2V1 and then 2V2. So, for these two vectors to be equal, that means the first coordinate has to be equal and the second coordinate has to be equal. So that means 3V1 plus 3V2 equal to 2V1 and then V1 plus 5V2 equals 2V2. Okay. So let me kind of move things around. The first equation that's gonna give me, let's see. I subtract 2V1 from both sides. I'm gonna get V1 plus 3V2 equal to 0. And then the second equation becomes V1 plus 3V2 equal to 0. Well, you can actually kind of see this is kind of the same equation already, but let me just kind of do the matrix thing. 1, 3, 0. 1, 3, 0. The reduced row echelon form for this guy would be 1, 3, 0, and then the second row disappear. So now my V2, this is my free variable. So the general solution for this equation would be negative 3 V2 and then V2. In other words, I can pull the V2 out. The solution for this matrix equation would be just V2 times negative 3 and then 1. In other words, any scalar multiple. So my vector V would be just every scalar multiple of, let's see, negative 3 and 1. In other words, the vectors v would just be in the span of -3 and 1. Okay, so these guys are the vectors such that when I multiply A by the vector, I get 2 times v. So let me actually kind of do this in the sandbox that we have earlier. So let me make this 3315, 3315. Okay. So if I make my matrix -3 and 1, let me kind of zoom in a little bit, -3 and 1, voila. You can see now the orange vector, the transform matrix, is actually twice as big as my black matrix. And it's not just this vector. As long as I remain on this line, as long as my black vector is a multiple of -3 and 1, as long as it's in the span of -3 and 1, my orange vector will always be twice as big as the black vector. We'll see next, this is actually not the only case when this happens. If I rotate this around here, my orange vector will now be 6 times as big as my black vector. But for now, let me give it an official name. Whenever this thing happens, whenever I have a square matrix A, and I multiply A by V, so I A times V. So that you can think of it as a linear transformation. I transform V. And when I transform that vector, it actually results in a scalar multiple of that vector. I get lambda. This lambda here, this is scalar. My V here, this is my vector. My V here, this is my vector. And my A here, this is the a matrix. A square matrix, actually. So, whenever this thing happens, the value for alpha, the scalar, the constant here, is going to be called the eigenvalue of a matrix A. In this case, the number 2 that we see here, this is going to be the eigenvalue of the matrix 3315 that we have. By the way, this is pronounced eigenvalue because it is a German word. The way we pronounce EI is kind of like the way we pronounce the word Einstein. And then the vector V that we see here, this is going to be called the eigenvector of the matrix A corresponding to the lambda. So any vector V that we see down here, any scalar multiple of -3 and 1, is going to be called the eigenvector corresponding to the value 2. So let me now move on to the next example here. I'd like to find all vectors v such that A times v equal to 6v. Okay, I can actually kind of do the same thing. I can just set my A times v1 v2 equal to 6 times v1 v2. But let me actually do a little different approach here. I need to have A times V equal to 6V. Let's see. Well, notice this V, is actually just the same as I multiply the identity matrix. In this case, it's going to be identity matrix of size 2 by 2 times V. If you don't remember I2, that would be just the matrix 1, 0, 0, 1. If you multiply, this is because this is the identity matrix. When you multiply this by the vector v, well, then you get the same thing. You get v. So my v here, this is the same as I times v. So let me just write it as I times v now. So I need to have A times v equal to 6i times v. Notice how this is a vector. This is a matrix, and my 6i. This is a matrix now. This is just 6 times the identity matrix. So, I can move my right hand side and my left hand side all together. I'm gonna have A times V minus 6i times V equal to 0. Again, this is a matrix multiplied by a vector. This is a matrix multiplied by a vector. when this happens, I can actually pull out the vector v. That means this thing is the same as saying that a minus 6i times v equal to 0. A minus 6i, which is a matrix, I get a matrix. I multiply this matrix by a vector, and I get a 0. So, another way of saying this is actually that, this means the v here, my vector v that make this equation came to, my vector v that make a minus 6i times v equal to 0, my vector v that make a v equal to 6v. These vector v's are actually belong to the null space of a minus 6i. Remember, the null space of whatever matrix is actually just those vectors that when I multiply them by the matrix, I get the 0 vector. I get the 0 vector. So this thing is the same as this thing. So this is essentially just what we need to solve. So, what is a minus 6i? A minus 6i, my a would be, let's see, 3315, minus 6 times I would be, which would be 1001. I do the subtraction, and that's gonna give me, let's see, negative 3 and 3 and 1 and negative 1. Now then, I can row reduce this guy already. This is going to be 1, negative 1 and 0, 0. So that means the null space for this guy, which is gonna be all the vector v that make a v equal to 6v, is gonna be the null space for this. The null space for the matrix a minus 6i is gonna be the same as the null space for this matrix here, which would be just the span of the vector 1, 1. Remember again, because this means I need to have my v1 minus v2 equal to 0, or you can see v2 as being a free variable, so my v2 can be anything, but my v1 is gonna be the same as v2. So which is kind of what you see here as well. For v1 minus v2 to equal to 0, my v1 has to equal to v2. So, all the vectors v such that a v equal to 6v is gonna be the span of 1 and 1. Notice how the answer for the two questions that we see here, these are not the same. For all the vectors v that make a v equal to 2v, those are the span of negative 3 and 1. And for those vectors v that makes a v equal to 6v, those are the span of 1 and 1. So then, notice how if you only talk about the eigenvector, it's not clear which eigenvalue these vectors belong to. So that's why when we call a vector an eigenvalue, we usually call it an eigenvector corresponding to a specific eigenvalue. So anything in this span is gonna be the eigenvector of A corresponding to the eigenvalue 2. Anything in any vector in this span is gonna be an eigenvector of A corresponding to the eigenvalue of 6.